Good morning, everyone. I have the pleasure of introducing Sacha Pos. He's an international student. Sacha Pos was born in Toulouse, in France, but was raised in the French part of the Basque Country. He arrived in Bogota 1 year ago. He earned a scholarship here in the Universidad de los Andes for a PhD in mathematics. Before he started this PhD program, he was studying mathematics in Paris, where he earning his bachelor and master degree. Sacha has given private classes to students with difficulties. He is currently doing a PhD in mathematical logic, more specific in model theory. Sacha is part of 2 research groups here in the Andes University. For him, being in Bogota is an important opportunity because here there are the large science or logical mathematics. Welcome, Sacha.
Thanks. Okay, so welcome everyone. Today I'm gonna talk to you about why size matters. So I like to start with this nice formula, which is graphically kind of aesthetic, I think so, and translates a really good, a really beautiful question in mathematics. So let's start with the size contest. Can you guess the size of the following sets? The first one is the set that contains only one number, 0.
Yeah.
So the size is 1. Okay. The next one is the set with 2 elements, 0 and 1. So the size is 2. Okay, we're going good. The next one
It's harder.
harder. 0, 1, 4, 18. This size is
4.
4, yeah, you're doing great. Okay, now go to the next one. We have 0, 1, 2, 3, 4, 5, 6, and so on until infinity. So this size is infinite, exactly. Okay, can we get an example that's harder? So now we have, we have all of those in this side, but we also take the negative numbers. So we are going infinite in 2 directions. So this size is also infinite, but it seems to be a bit bigger, or not sure. Okay, the last one is even trickier. We get the interval 0, 1, which is all the numbers that are contained between 0 and 1. I mean 0.5, but also 0.59, 0.34, all of the numbers you can imagine between 0 and 1. So this one is also infinite, but it's bounded, so it feels like it should be smaller. We cannot really imagine what is the size of this. So if there are many sides of infinity, which is the subject of the speech today, how can we measure the size of the sets? So we have a great tool for that. That's the notion of bijection. A bijection is a one-to-one correspondence between 2 sets. Let me explain myself. We have a set X with, in this case, 4 elements, and a set Y with also 4 elements. So we are sending one element of the set X to another one, and we're doing that for every element. That's called a bijection, or one-to-one correspondence. Okay, so this man, George Cantor, gave birth to the previous tool and to the question that we are going to study today. So in an article that he published in the early 20th century, he gave a first really strange result. That is that the set of rational numbers this is this set, all the fractions that you can imagine, so 1/2 minus 2/5, 18/47, is in bijection as the same side, in other words, as 0, 1, 2, 3, 4. So that's a bit strange. It seems that you have a lot of fractions, but you don't have so much natural numbers. But it proved that you did. Okay, and then it gave a really disturbing result. The interval 0, 1, which is represented over there, has greater cardinality than the natural number. That means that if you try to send the elements of this set on this one, you're gonna miss some of them. So it's strictly bigger. And that started a war in mathematics, really. We have two sides of the war. We have the team A, which is represented by David Hilbert, another German mathematicians that believed in Cantor, that said that Cantor was totally true with his point. And the other team, Team B, which is represented by Henri Poincaré, a French mathematician who said, no, that cannot be true, there's one infinite, infinite is infinite, you cannot have many sides, that's totally crazy. And guess who won the war? Team A, which is David Hilbert and George Cantor, with this marvelous sentence, no one shall expel us from the paradise which Cantor has created for us. It's really beautiful. So the next question is, can we classify infinity? So we have a smaller infinity, which is Aleph sub 0. That's an Hebrew letter, which is the A of the Roman alphabet. So let's say that this is the size of the smaller infinity. That's the size of the natural number, 0, 1, 2, 3. It is indeed the size of the relative integers, the one that you can put a minus in front of them, and then you get all of them. You can also know that that's the size of the rational numbers. That's the first theorem I gave you earlier, all the fractions. Okay, but now what comes next? We call the next size of infinity Aleph sub 1. Okay, it makes sense. The first one was Aleph sub 0, so the next one is Aleph sub 1. So we have this inequality. This infinity is smaller than this infinity. But what about the size of the interval 0, 1? Is it bigger? Okay, it has size 2 at Aleph 0, which was the number that was written in the formula in the first slide. That is strictly greater than Aleph sub 0, so it's not the smaller infinity, but can we compare it to Aleph sub 1? So we get to this question, is 2 Aleph 0 equal to Aleph sub 1? And actually we don't have a really good answer. And can it get weirder now? Yes, it can. It is independent. It was proved by Kurt Gödel from one part and Paul Cohen on the other side, that the continuum hypothesis, which is the name of this famous formula, is independent. What does it mean? That means two things. We can add this equality to the traditional axioms of set theory, and we are not getting any contradiction from that. So okay, but now you can add its negation to the same axiom. That is that the equality is not an equality, it's not true, and you don't get any contradiction. So we say that it's independent because it cannot be proven from the axioms of set theory. Okay, that's all I'm gonna talk to you today. Just remind you that this was what gave birth to the logical mathematics, kind of, and that's why I'm interested in that topic. Okay, thank you.
Thank you.